out the equation, right? We make sure that what's on the left equals to what on the side. It's like a balance. You come from the Caribbean, you know when you go to the shop, you get a pound of flour or a pound of, they put it on a scale, right? And they put a weight on this side, and then they pour in, and sometimes they cheat you. Because to make sure it's like kind of leaning towards the weight, and then take it off quick and cheat me, right? But me, no, that must be balanced. Put in 2 more grains. That's what I'm paying for, right? But you see that if you're from the old school, coming to the Caribbean and stuff like that, you understand balancing, right? Because we don't use digital. Well, maybe today they don't, but we used to use the big old
scales, yeah, the big scales.
Big old scales. Man.
And you had to take the thing and bring it down this way, you know.
They used to cheat you though, because they used to put that kind of thing under the thing and make it heavy on that side. So here's the deal, right?
It's true.
Hey.
You.
We had a shopping now. Don't play with me. I know the games. The equation must be balanced. All the atoms of every reactant must also play in the product. Right? So you can't miss anything. It must, what over here must show up over here. Must. Right? Can't go anywhere. So here, what we have is 2 hydrogens. I'm saying hydrogen. 2 mercury, 2 oxygens. On the left, 2 mercury, 2 oxygens on the right. It's balanced. It's totally balanced. Right? Here's the deal. How do we call this out? We say 2 moles of mercury oxide reacts, decomposes to produce, to yield, or to give 2 moles of mercury and 1 mole of oxygen. This 1 that's missing here is understood. 1 mole of oxygen. Notice how oxygen is written as O what? Right? It's in combination here, it's just O right, because it's in a combination, but when it's by itself, it has to be a diatomic molecule, diatomic atom, a diatom, however you want to call it. I don't care what you call it, just know that that must be true. Okay? Alright, here, very simplest reaction ever that we know. H2, see how it's written? Hydrogen is one of them 7. Oxygen is one of them 7. H2 plus O2 gives you H2O.
No.
Huh?
No?
No? Oh. Water, wait.
Go to this. H2, hydrogen gas, plus O2 gives you H2O.
2O, yes. Agree.
100%.
Oh, yeah, but
How? Because it has to be balanced.
It has to be balanced.
Because we know oxygen and hydrogen gives me water.
I know.
Right? So now, here's what we have to do. It's not H2O2, it's not hydrogen peroxide. This H2O2 is hydrogen peroxide. Hydrogen and oxygen don't give us hydrogen peroxide. Okay? So now, you cannot balance this thing here to change the subscript. You never touch the subscript. Don't do it. We don't balance from the subscript, we balance from the coefficients, right? So here is what we have to do. We count the number of moles of atoms on each element on both sides, reactants and products. We see we have 2 hydrogens, 2 oxygen, 2 hydrogens, 1 oxygen. Something is wrong. How do we get 2 oxygens here? Right? We have to figure that out. How do we really balance this thing out, right? Because here you can begin to see I needed 2 as a coefficient in front of H2O. But notice when I put a 2 in front of that guy, I changed the number of hydrogens. Because now it's 2 times 2 gives me 4, 2 times 1 gives me the 2, so I'm good with oxygen. But I only have 2 hydrogens here. So I now have to balance out again, right? So when I'm balancing, I'm looking at it, I'm like, okay, I need a 2 for my oxygen. Normally it is this subscript that tells you what you need. See this 2 here? That's a way of looking at it. This 2 tells you I need a 2 in front here to get them 2 oxygens. But it changes my hydrogens. So it's not balanced. Hydrogen is not balanced. To balance hydrogen, I got to put a 2 in front of the hydrogen, not the subscript. Notice I'm not touching the subscript. So 2 times 2 now is 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. 2 times 1 is 2, gives me my 2 oxygens.
I was saying it wasn't balanced. I was saying.
I thought you were saying 1 H2 plus 4 to give me H2.
No, I was saying it wasn't balanced.
I was like, what? What else going to give me that? Okay, so then you have to make sure that conservation is observed, conservation of mass, and you go back and this is how you do it. You make the check. It's balanced now, right? Because whatever is on the reactant side is on the product side. It's a trial and error. Sometimes it break your head. But what I was trying to tell you, and what I would tell you early, right, is that certain reactions, you don't mess with oxygen. Especially combustion reaction, balance everything else, oxygen falls in place. Okay? This is a simple guide that we try to balance oxygen, right, first. But you never really do oxygen first. You would not sleep the night. Okay? I'm talking from experience as a student. Alright? So balancing chemical equations is very simple, right? You just have to make sure it's the coefficients you're messing with and not the subscript. Do not ever touch the subscript. Don't do it. Okay? Alright. So here is a let's look at this is a combustion reaction, right? Here you see this is a gas, ethane gas. Right? No, it is ethene gas, right? This is a gas here, ethane gas, right? These are 2 combustion reactions. This is
like
again,
ammonia,
like water, right? Ammonia is the Haber process. Ammonia and hydrogen gives you
Combination.
nitrogen and hydrogen.
gives you ammonia.
Okay? This is a particular, this is a synthesis or combination reaction. What is this one? Combustion, right? Once you see oxygen involved and you see a CH, right? This is a gas, this is a natural gas, right? And then here, what would this one be?
Double replacement.
Double replacement.
Okay.
Alright, so let's attack something here. Let's look at the combustion reaction because those are the ones that are kind of tricky, right? We have C2. What? Okay, you want to do your own thing. So you have C2, H2 plus O2 goes to CO2. Notice that the combustion reaction, the products are what? Carbon dioxide and water. Okay? It's a complete combustion, right? If you have an incomplete combustion, you are going to form carbon monoxide plus carbon dioxide plus water, right? So that is why they tell you in the wintertime, if you don't have no heat in your house, what they tell you to do?
Turn on the gas stove. I'm sorry, don't use.
Just tell me where you live so I can send that.
No, don't use the gas stove.
Right, they tell you go
Yeah.
to shelter.
Yeah, go
right?
to shut. Yeah.
But the reason why is that when you don't have heat in your house, I've done it, right? And thank God I survived that crap. As a young guy, I would admit that.
It's happened to all of us. Yeah.
What happens is that you're cold as hell. You ain't gonna leave no window open.
True.
Because they're trying to get rid of that cold. They turn on all your burners. You turn on the oven, rip down the oven, tell God it's cooking, and you go to sleep. What's happening is that this gas is competing with you for that oxygen. Because that's what you need to survive. But this gas needs that to burn. And when this gets depleted, because that becomes a limiting reagent, because you lock down the whole place, so you lock in a limited amount of oxygen, then this doesn't form, you have CO, and you just sleep. You never wake up in this life. You're waking up somewhere. So that's why, seriously, do not do that. Right? Do not do that. I wouldn't even tell you to leave a window open because it's still dangerous. Right? You need you and the gas fighting for this. And at some point, the amount of gas that you lock up in the house, the amount of oxygen you lock up in the house, is going to get depleted. When this can't get it, and you can't get it, this guy's building a poison, it's producing a poison. And it's a silent poison. And the funny thing about your body holds on to CO, right? Your heme group in your blood that transports the carbon dioxide and the oxygen back and forth for cellular respiration. It loves CO more than it loves O2. It binds tighter to this. So it would be like holding on to that, and it's killing yourself. That's how you die. Okay? Alright, so now, when I do this reaction, I like to tell students, put a box in front of the substances. Why do I want you to put a box in front of it? So that you don't go and mess with this. It's a reminder that I have to deal with this and not these, right? Just a quick reminder. Okay, so here's the deal. Bam. If I look at this, I have 2 carbons, right? I have 2 hydrogens, and I have 2 oxygens, right? Here I have 1 carbon,
Oh God, I can't see that.
3 oxygens, 2 hydrogens. That's unbalanced, right? I have to figure out how do I balance this gas. Because this is a combustion reaction, I'm not messing with the oxygens. Like I tell you, don't mess with the oxygens. I did it when I was a young student, and I never slept the night. Okay? Because it beat the crap out of me all night. Right? Started at 9 o'clock, never went to sleep. Right? Because it was that intense. I was pissed. Couldn't get it out. And then my professor told me the next day, I came to him early, really bloodshot eyes. He said, man, what are you doing? Don't balance oxygen. And he did it in a second. I was like, shit. So, here we go. There's 2 carbons, there's 1 carbon. There's how many hydrogens? 2 hydrogens. So hydrogens are balanced.
I can't see, Professor.
So, then move.
What do you mean move? You got this big computer in the way.
So you must move the
Move.
You know. Chuck.
All right with that woman there. You have to move and go by the garbage can get out. So here it's 2, right? So I put it 2, so then I have to change this to 2 carbons, right? So far my carbons are good.
I can't.
Correct? 2 carbons, 2 carbons, right? But what that did to my oxygens, it changed my oxygens as well. So 2 times 2 is 4 plus 1.
5.
So that becomes 5 oxygen. Knock that off, right? But hydrogens are still okay. So fine. Now, here's the deal. Since that I have 5 oxygens, what number I can multiply by 2 to give me 5? Practically no number.
No number.
But I can use a fraction.
So why make it so hard?
So how easy is it going to make it?
No, why make it 5?
A fraction. Oh
So
my God.
because if I put a 2 here, it's going to knock out my hydrogens, and now I have 4. And if I put a 2 here, then it's going to knock off my carbons again, right? So now, one of the things that you have to do when you're dealing with combustion reactions is you have to use fractions.
Oh, okay.
God.
Right? It's the easy way. It's the easiest way. The only way. Right? So now, what number is, I have 5, right?
2, yeah. 2.5.
Don't look at me.
Right? So what can I,
To make it 5?
yeah,
2.5 times 2. So put 2.5 in the box.
okay. So can I represent 2.5 by a fraction? You might do decimal.
Oh, yeah, okay.
Can you
5 over 2?
5 over
over
2.
two.
Okay.
2.5 can work, but I think in,
Okay,
I think in
Okay.
fractions because
Okay.
fractions are easier than decimals for me.
Alright.
That's just me. Might not be for you, but this is how I was taught, right?
Okay.
In terms of fractions.
Okay,
So
fraction.
now here, 5 over 2, right, times 2 is really equal to
5.
5.
5. Okay.
Because that cancels out and it's just 5, right?
Okay.
So now I have 5 over 2, right? So then my oxygens move to 5.
Yeah.
5 oxygens. So I have my 2 carbons, my 2 hydrogens, my 5 oxygens. Right? Make sense?
Yeah.
Okay. However, I cannot represent
Fraction.
my final equation with a fraction. So the only other thing I can do is multiply through the whole equation. Again, this is when you have this combustion reaction there, pain in the ass. I'm going to multiply by 2. Because if I multiply by 2, I create a fraction. Okay? So if I multiply that by 2, right, this now becomes 2 C2H2 plus 5O2 goes on because the first fraction clears, right? I multiply by 2. 4 CO2 plus 2
No, sir.
H2O. Okay? And that balances the equation, right? So when we look at it, now we have 4 carbons. How much we have here? 4 carbons. We have 4 hydrogens, right? How much we have here? 4 hydrogens. We have how many oxygens? 10 oxygens. Stop saying you can't see and go move to a place. I can't help it, my dear. Talk to the president. Tell her you're losing a lesson.
How your ears so clean? Oh my God, I was whispering. You heard?
You have to make sure people don't feel okay? Then we have now 4 times 2 is 8 plus 2 gives me 10 oxygen, right? It's the bookkeeping, right? You have to, but what you have to remember is when you're dealing with combustion reaction, we have a carbon with an oxygen. If it's not coming out clean, you may have to use a fractional coefficient, and at the end, you have to clear the fractional coefficient by multiplying the whole equation by the denominator of the fractional coefficient. Right? Okay. All right. That one was very nice.
Oh yes, it was. It was fantastic. I loved it.
Only that you can't see. Yeah. Okay. So I mean the others. Let's jump into this one. Might be easier, right? We do that one, and I'll leave the rest for you to play around with, right? I like to do the ones that are a little challenging, so you can see. So we have ethane, C2H6 plus O2, and that goes to CO2 plus what? H2O. Yeah, I put a box in front again. Always do that, right? So that my students really pay attention to the fact that they don't play with the other stuff. So here I have 2 carbons, 1 carbon, right? Again, I'm going to mess with everything. I'm going to mess with hydrogen first. I'm going to mess with carbon first. Never touch oxygen, right? I leave oxygen for last. So here I put a 2 here. So now I have carbon, 2 carbons, 2 carbons, right? When I did this, right, I changed the amount of oxygens I had, right? Because 2 times 2 is 4, right? 4 plus 1 again becomes 5. That's problematic, but let me give you my hydrogens first. There's 6 hydrogens here, there's only what? 2 here. So if I put a 3 here, right, I have 6 hydrogens here, 6 hydrogens here. Now let's see if the oxygens flopped into place. If not, we're going to have to do our dynamics, right? Here, this is what? 3 oxygens, that ain't working, 2 over here, right? So, what number can I multiply here and here? What do I have to change, right? I have to pay attention to that. How many oxygens do I have? I have.
You have 7.
How many oxygens I have?
4.
4 plus
3.
Yeah.
7.
7 oxygens. So what can I multiply with to get 7 oxygen?
Well, 3.5 again.
7 halves.
16.
7 over 2, right? It's always 7 halves. It's going to be some number over 2, right? Because 7 times 2 is
15, 14.
Yeah, I'm telling you, this. Hey, listen, I'm going to stop coming here. So that is equal to 7. So that gives me the 7. 7 halves, right? But then I have to just clear with the fraction, the numerator. So that becomes 2C2H6 plus 7O2 goes on to give me 4CO2 plus 6H2O, right? Here, let's check. I got 4 carbons. I have 12 hydrogens. I have 14 oxygens. I have 8. All right? You gotta practice. You gotta do. You gotta give it 2 problems. There are 5 problems in this set. Do all 5 of them. Give me the 2 I asked for. Keep the 3.
Originally, the product, you had 1 carbon, but you put 2, where does 2 come from?
The 2 come from here. There was 2 here, so I have to put the 2 here.
When it's CO2, the C has 1 carbon.
Right, that's what I'm saying. C
So,
has 1
but
carbon.
in the first
and the
part,
first one has
it's
2.
C2.
But you don't see the equation here. You don't see 2 carbons here and 1 here.
That's why I did that first to make sure 2 is over there.
You don't see that? That's why we're doing that. This is why you're doing it.
I know.
You sure?
Yeah.
Really?
Yes.
Cool. All right. Once we sure. Okay, let's move on. Precipitation reaction, right? Changing the chemical solution that results in 1 or more insoluble products. You're going to have to now use your memory. Your memory is going to come into play right here, right? To predict if a precipitation reaction can occur, we have to know the solubility rules. This ain't given to you on no test or nothing. You must know this, right? Here are your solubility rules. You have to learn this. Right? Well, you know what? Here's the deal. When I was sitting there, I had to learn this. You sitting there, you're gonna learn it.
So could you teach us how you learn it?
What you are, you're doing chemistry, right? This is your problem there. Okay, so here's how this works, right? Solubility compounds, right, contain alkali metals, which are group 1 metals, or with ammonia, they are always soluble. So anytime you have a compound that you have lithium, sodium, potassium, rubidium, cesium, and ammonia, the polyatomic ion, the compound is solid, which means it's in the aqueous phase. Aqueous, right? Ammonia, right?
You said ammonia.
Right? Huh?
Soluble.
Yes, I did. And you corrected me, and I corrected you.
Soluble compounds.
You said group 1?
So, group 1, yeah, all group 1. If the compound has group 1, it's soluble, right? It's aqueous, it's in the aqueous phase. Nitrate and bicarbonate, right? Or the chlorate. If your compound contains these guys, it's soluble, which means next to it, you put AQ, which means
Aqueous,
right?
yeah.
The halides, right? But here's the halides come with an exception, right? So you have chlorine, bromine, iodine, but if they're in combination with silver, mercury, or lead, they're going to be insoluble. So you put an S next to that compound, which means you form a solid, right? The sulfates, all sulfates are soluble except when they are in combination with silver, calcium, strontium, barium, mercury, or lead. That's the exception. See, everything else, only halides and sulfates have this exception. So this is what you really have to pay attention to. Now, insoluble compounds, they're insoluble off the bat, right? Carbonates, phosphates, chromates, and sulfide. They're insoluble, no matter who they combine with, except when they're with group 1 and ammonium ion. If they're with group 1, if these guys are with group 1 and the ammonium ion, they are soluble. Other than that, they're an insoluble compound. Right? The hydroxide ion, it is going to be insoluble. The only thing that makes it soluble is the alkali. See how these guys, they have a lot of power, right?
Yeah.
And the barium ion. Those are the only two that will make this. These guys and barium will make this soluble.
Let me ask a question, just to let me ask. So with the with the insoluble compounds contained, right? The carbonate, the phosphate, the chromate, the sulfide, and the hydroxide. Is it because they form bubbles?
No.
Oh. So how does it become insoluble? Like, what's causing that to be that way?
What's causing them to
the carbonate.
become insoluble,
Yeah.
right, is because when they bond with these other substances other than these, that physical property that or chemical property that contain causes them to not dissolve.
Oh.
They do not break up into the ions. Like when you have, for instance, I showed you, when you have sodium and chlorine or sodium and nitrate ion, right? You can separate them into Na plus and NO3 minus.
Okay.
Right? Where are my nitrates? My nitrates are right here. My sodium is right here. So when these two guys come together, they're insoluble.
Okay.
Right?
Yeah, the sodium, okay, and the nitrate. Okay, got it. Okay,
Right?
okay.
So you guys have to know this. In order to do some of these writing chemical reactions, because in writing chemical reactions, you have to know who is soluble, you have to know who is insoluble, because the next step is to write what we call a net ionic equation that gives us, it's not every single atom really participates in the chemical reaction. Some are spectators, and we don't care about them, but we have to know who is spectators so we can focus on the species that is really reactive, okay? That's where we're going to go right now. So here, we have to predict when precipitation will occur, right? And we have to look at the rules in table 4.1. Any insoluble salt will be a precipitate. Like we know lead. Go back to the table. Lead with chlorine is insoluble. So right here we know when this is soluble, because it's a nitrate, right? This is soluble because it's a group 1 and it's a halide. But here, because this halide is not with a group 1 or ammonia or nitrate or one of these guys, we have a problem, right? So, but we know sodium and nitrate, they form soluble compounds. So here, this would be aqueous, this would be insoluble, which is solid. Right?
Oh.
So now that's where we stick this in, because going back to the table, right, we know that lead and chlorine combined is the exception that makes the compound an insoluble compound. So here we get the solid, and here we get the aqueous. This tells me a chemical reaction occurred. Because if I do this, and I have all aqueous forming on my reactants, no reaction took place. If I don't have a gas, no reaction took place. Okay?
Yeah.
I have to have one of these. Remember, go back to the 4 things we said. Color. We had some temperature. We had precipitate, and we had gas formation. Those are what? Here this solid tells me it's a precipitate, so a reaction took place.
So you don't need water for this. This is just between chemical reactions, right? No water doesn't have to be used.
Water will show up as a liquid.
As a liquid.
It's the only liquid. Pure liquid. Okay?
All right, okay, yeah.
So I'll leave these to you so we can move forward, right? Potassium chloride and silver nitrate. What does that look like? Let's just knock one of them out so you see what the process is. We have potassium. What's the
K plus, K positive, sorry.
You sure?
Positive K.
You sure?
Yeah.
You sure it's not P?
No, it's K.
Okay. Okay. You have K and chloride. When potassium and chlorine come together, what is the formula?
Potassium.
KCl.
KCl.
KCl. And is it aqueous solid or liquid or gas?
Potassium, chloride, aqueous.
It's aqueous because it can be broken down into its constituent ions.
Yeah.
Plus, we have silver nitrate. Silver,
Ag.
Ag,
G. Mm-hmm.
And will negative.
Silver.
NO3.
What are we doing? Potassium acetate. Yeah.
Just NO3.
NO3.
Right? When we have compounds, we can't put charges in them, right?
NO3.
So, if we have these two guys, what are my products? What is this type of reaction in the first place? Kind of reaction is that identify, double replacement. So potassium gotta go with sodium and silver must go with chlorine, right? That's the AB plus CD. What we have is the AB plus CD, and it's going to go to AD plus CB, right? All right. So now all of them is a 1-to-1 because this is a negative one, this is a positive one, this is a negative one. It's a 1-to-1 ratio. So we just write them as is. So we have K, NO3, and we know that this is aqueous because it's a nitrate and it's a +1. It's a group 1, right? And then we have what? +1, silver and chlorine.
So that's the solid because the exception is the silver.
That's right, silver, lead, and so forth, and mercury, right? So now this is just solid. That's how you do it. We gotta go back to the rules. You gotta know what is formed. That is why everything builds. That is why we have to know the different type of reaction. We have to know what signals the chemical reaction took place. We have to know how we combine them. We have to know the solubility rules because it tells us who is solid and who is aqueous. Right? Everything we do, it builds. And if you pay attention, you're seeing how it just stacks and builds. All right? Net ionic equation, that's right where we're going right now, right? Because not every single substance in the reaction really takes place. The spectators, right? I'm thinking about some of my kids, man, from years ago, you know? I have a lot of kids. You know the more the kids are coming through me? You know the more the kids are coming, you know the more the kids, thousands of students come through me. When I talk about my kids, I talk about my students. If I'm talking about my seed, it's my children. If I'm talking about those who have interacted with my scholars, are my kids, you know? Now, when I think about spectators, I had a couple of them who got caught up in some nonsense that they were doing.
Sorry,
They were gangsters. And as much as I tell mommy and daddy that they're gangsters, they weren't listening, they ended up doing some horrible stuff. But they were, and they had spectators, they had active players, so they were using my camera. I'm like, whoa, what's wrong with you? Nah. But it's life, you know? It's just life. Okay, so this thing is balanced, right? It's a 1-to-1-to-1-to-1, right? Now, when we look at the, we know what our soluble substance is, right? So when we look at net ionic equation, spectators ion do not participate in the reaction. So we're trying to get out all the spectator ions and only focus on the ions that are taking place in the reaction, right? So here, what we do, right, once we know who is aqueous, we can break them down. Remember, they have to balance it just right. Remember I just said it's 1-to-1-to-1, so it's balanced, right? Maybe some of you missed that. But if it wasn't balanced, I'd have to balance it, right? Otherwise it will work out the way we want it to work out. So here, because potassium chloride is aqueous, I'll have K plus, right? Aqueous, plus Cl minus aqueous, right? Plus And if this had a 2, it would be 2 potassiums, 2 chlorines, because the 2 is affecting it, right? You still have to put it in, right? Plus, I have silver is a +1, is aqueous, right? Plus the nitrate ion, right, is aqueous, right? Then that goes on to give me my potassium nitrate, again, which is an aqueous compound, so I can break it into its component parts, right, or component parts. This is a minus. But this guy, I cannot break liquid and solid. So if you have water, you can't break water, because water doesn't ionize.
Wow.
Right? You can't break up water into H plus and O minus. You can't do that. Right? It's a compound. It's a covalent compound.
Yeah.
Molecular compound. Right? And then I would have AgCl solid. Right? That's the ionic. This is the ionic equation. That's the ionic equation. So now I get rid of my spectator ion. My spectator ion is any ion that shows up on this side that's also on this side.
Yeah.
Right? So when I look, I see my potassium, strike my potassium out, right? I see my nitrate ion, strike my nitrate ion out. Those are the spectators. They do not help or aid in this reaction to form my product. So my net ionic equation is going to be my silver, Ag plus, aqueous, plus my chlorine, right? That goes to give me my AgCl solid. This is the cold reaction. When I don't do all this fancy stuff, these are the only things that are reacting to bring about the product that I get out of this reaction. Okay? Alright? So you have your general equation, that's your equation, your chemical equation. Then you get your ionic, right? Your full ionic, and then you get your net ionic. This is what the questions are after, right? When you get that net ionic equation question, that guy right here at the bottom. Not all this nonsense up here, this is what they want you to tell you, right? So now you can see it's balanced for mass, right? One silver, one chlorine is also balanced for charge, right? Plus negative gives you 0. Over here is a full 0 on the AgCl, right? So we're really balancing. When we balance the mass and balance the charge. Okay? So we deal with charge, balancing the charge, making charge, as we do redox reaction. Okay. So this is what I just did. Right? The steps. Write you write the equation, write the ionic, write the full ionic, right? And then you write the net ionic equation. And that is where our thing is. Everything is balanced, charge is balanced, right? Again, if you didn't see, it's a plus, minus gives you 0 on this side. When we form compounds, we don't have charges on compounds. It's 0. They're in the 0 state, right? Right? See, this stuff is like water. Okay, acid-base reaction. You know, I used to feel like it, but because I didn't study and I was playing around and I was doing this and then I had to come back and, double up on my time. That's what I used to think it was on. Then I got smart. So while my friends are having parties and I go to the party and Saturday night, I go book bag and I say, yo, let me just, I'm feeling tired. Let me just, give me a few minutes now. Let me use the bedroom. I go in there doing my work. Party going on, everybody going on with this stupid. I come back out like about 4 o'clock. My work done do. They say, yo, Charles, you going to do this work tomorrow? No, Charles sleeping. Charles don't partying. Because we done my work. That's what you
True.
I think it's true.
No, it's true, you're right.
That's how I used to do. I had to get my stuff done. And then a party, but while I'm at the party and they're hanging, I go in the bedroom and I do what I do. Find a spot.
What year do you think this is?
Yeah, exactly. I need to know.
You know, here it was when I was doing it. It was a year to get my damn degree and get out to school. Some of my friends in them who was partying, they still not graduate up to today.
It's true, you're right.
Okay.
Yeah.
It takes a special fund to get a PhD in chemistry.
We're not even talking about PhD, man. We're talking about the undergrad.
To go that far, and just...
Look, it's a terminal degree. What, 1-2% of people in the world have it? Right? You can be one. Right? Anyone in here can be one. You just gotta put your mind to it. Right? It's that with a PhD, you're teaching yourself. Nobody's teaching nothing. You know what I mean? You're showing the world, you're showing the department, you're showing your mentor, you're showing your committee that you can learn by yourself and you can develop a thought by yourself. That's all it is.
And that's what the thesis is, right? That's what you have to, okay.
You have to be convincing.
Yeah.
You have to tell a story.
Story, yeah.
You got to get data. When you get the data, you got to say, this is what the data is saying. And you have to be so clean with it that everybody believes that shit.
Wow. That's good.
But you have to why you gotta get everybody to believe it, or just keep sending you back.
Right.
Make them believe it.
Believe it,
You
yeah.
understand?
Wow, that's great.
That's all it is. That's all it is. Once you get to the coursework, it's just making people believe this shit is for real. He's a genius. And you're like,
Got it.
struggling
Yeah,
with,
that's good.
I'm going to say this, right?
No, it's
so
true.
anyway, acid and base reactions. We spoke about that. You saw this one. Hydrochloric acid is one of the strongest acid. I keep saying one. It's strong. Sodium hydroxide is the strongest base. So here we have a strong acid, strong base neutralizing. Notice now where water comes in, right? I said earlier, water is the only liquid you're really going to see written that way. Nothing else, right? So here you have the H plus ions and HCl was transferred to the oxygen, right? In OH minus to give you H2O. That's what's happening here. This H plus displaces the sodium. You get HOH, but HOH is nothing more than H2O.
Okay.
Right? So then you get the neutralization. This is the neutral product, right? It's not acidic. It's not basic. It sits because the water is about 7, pH of 7, right? All right. We talk about oxidation. So that's just, we saw the combustion, right, in balancing, and we see the neutralization here in one shot. That's all they got for us. Remember, we have to, later down, we're going to see what acids are, what bases are. These are inorganic acid bases and inorganic acids, because we do have organic acids and organic bases, right? Our body built from these things as well.
Your hydrochloric.
Okay, here, oxidation reduction. When we think about oxidation reduction, right, we have to think in terms of who loses electrons and who gain electrons. When I was going to undergrad, it was about oxygen. Oh, that was difficult. And some smart aleck changed the whole, but it's still about oxygen, right? About oxygen, who gain oxygen, who lose oxygen, all kind of stuff. But it's really the electron, right? So we have to think about the loss of electrons, loss of hydrogen atoms, gain of oxygen atoms. See, that oxygen thing, I hate it. But this is where it really is. But when we look at the half reaction, right? Magnesium, any element by itself and combined has an oxidation state of 0. Okay?
Any element.
Any element sitting there by itself has an oxidation state of 0. Then here, when it interacts with another substance, it changes oxidation state because now it becomes combined. So in this case, magnesium becomes a 2+, because for it to interact with someone else, it must be an ion. Right?
Yeah.
Can't be in its natural state anymore. So then it becomes 2+, but you have 2 electrons that are involved. It released 2 electrons. That's why it becomes the 2 plus. Remember going back to how we calculate the number of electrons, the number of protons, how an ion becomes an ion and so forth. This is what coming back at you right now. So if we have a 2 plus, then it did lose 2 electrons, right? So it moved from a 0 oxidation state to a 2 plus oxidation state. Okay? Now, how do we know who is oxidized and who is reduced? Who is the oxidizing agent and who is the reducing agent? It's the flip side. It's just a flip, right? Leo says girl. That's a Leo the lion, right? This is just loss of electrons. It's going to be oxidation. That's an easy way to remember. That's an acronym, right? To help you remember. Leo the lion says girl, right?
I wish I could see, but go ahead, I'll listen.
He said girl. Them shit don't say girl. That's all. They're raw, right? Just remember something when I was in Africa. Them lions, boy, them Africans them lions, and them lions right there, you in a truck right here, that's open. I'm like, yo man, who's that damn truck? Yo man, yo man, move this truck, man. I see enough of them Moses lying down. Just say, oh, they can't see you. You just don't move. I'm like, yo man, move this damn truck. I'm like, right here. Yo, so, Leo the lion is girl. Loss of electron, it lost 2 electrons. It was oxidized.
Oh.
Okay? That's how we look at it. That's easy, right? To figure this out. Don't kill yourself. Look at the fact that it moved from a 0 oxidation state to a charged state. It had to lose electrons. It was oxidized. Okay? Now, for instance, look at chlorine, right? Now Cl2 plus 2 electrons. Well, we know when anions or when atoms take in electrons, right, they become negatively charged. So you get now 2 Cl minus. So it's 1 oxidation state, right? What this does, this guy was oxidized, right? So here, right, gain of electrons goes to the cyanide oxide reduction, right? Right? Go. So GER, gain of electrons, is a reduction. You can see it gained 2 electrons. Where is it written? On the reactant side. Where are the electrons and the product?
Okay.
Ah.
Okay? That's how, so we call this one the reduction half reaction. Right? And this is now the oxidation.
Which is the loss of electrons.
Yeah.
Okay.
Half. Okay? So questions can just ask you for the half reaction, or they can tell you to write, one or the other. Right? So this is how we look at it. Here we have the reduction half here. Look at where the electrons are written. Right? And if you put these 2 equations together, then that electron is going to negate this electron because they cancel out each other. Right?
Isn't that basically oil rig?
Huh?
Isn't that basically, well, in bio, we learned oil rig. So that's what it is, right?
That's how they, in bio, they do it. Chemistry do it in chains. Bio, I don't know how they do it. You understand that. Chemist does it in chains. I don't know what biologist doesn't do. I don't have to ask my wife, because she's a biologist.
Oh, excuse me, Lord, you don't.
I'm out of science. Yeah, kind of. Yeah, she keep on to my chemistry, keep going to her bio. We only interact when certain times.
Oh, you do chemistry and bio.
She can do chemistry and I can do a little bio.
Oh.
But and then Edison he just like I like both, so he became a biochemist.
Oh.
That's right. He became They all do science though. Except my daughter, she got lazy. She went to social science.
It's okay. Yeah, right? I'm tired of y'all.
She said it's still science, yeah. I'm like
Social science.
social science. Yeah. But she does good.
Yeah, she's doing good.
Anyway, here. So we look at the 2-half reactions and we build the full reaction. So you can see the full reaction here. Notice that it's balanced for charge and it's balanced for mass. Here we have the Mg and the Cl, right? Notice the 2 electrons do not show up. They don't show up in the equation because they're spectators like, right? So we get rid of them and what we have is a Mg2 plus and 2 Cl minus. On this side, it's a 0, right, charge total, and on this side it's a 0 charge total because the 2 Cl minus or the 2 minuses cancel the 2 plus, so it's 0. So it's balanced for charge, it's balanced for mass, right? Now, here's the deal though. Reduction half and oxidation half, one species causes the other one to be reduced, and the other species causes the other one to be oxidized. So we talk about the oxidizing agent and the reducing agent. The oxidizing agent is the one that was reduced. See the flip?
Yeah, that's how it
See the flip? If you know who was reduced, that's the oxidizing agent. If you know who was oxidized, that's the reducing agent. One causes the other. They exist, they coexist together. Right? So if you have an oxidizing agent, you must have a reducing agent. If you have a species that was reduced, you must have a species that was oxidized. But who caused the species that was reduced to be reduced is the oxidizing agent, which is this guy reduced, and that causes the reducing agent to become the oxidizing, the one that was oxidized. Just a flip, right? Notice.
Okay, so you could use the reducing agent to oxidize, or you could
the reducing agent is the species that was oxidized. The oxidizing agent is the species that was reduced.
Okay, all right.
They happen. It just.
But you could do it in reverse, meaning you could do either one to either one, or it's no.
This is set.
Oh.
Because the oxidizing agent gained electrons.
Okay, got it.
Right?
Okay,
The
yeah.
reducing agent lost.
Loses electrons.
Yeah.
Okay, got it. Good. Okay, yeah. All right, cool.
All right.
Yeah.
Voltaic cells. Yeah. Well, here's this. Because they had a week off.
Yeah, I need some coffee.
You have a week off. When we think about voltaic cells, right, we're talking about batteries.
Okay.
Right? Batteries, actually.
Yeah, voltage.
And this is the basis for the lithium battery. It's the basis for the regular AAA, AA batteries, right? Zinc, when we look at what goes on, these two species don't have to be in the same space or mixed together for this to happen, but there's certain things that we have to have. We have to have like cathode and anodes, right? That are in the solution, and we can cause electrons to flow across a wire, right? So in this case, when we look at zinc, if you don't see a charge on top of the species, they're in the natural state, they're 0. right? Oxidation state is 0. So here zinc moved from 0 to 2 plus, which means that it lost electrons, it was oxidized. Leo says, girl, oxidized, lots of electrons oxidized. Cu2 plus here, this was in combination with something because how I know? Because it says aqueous.
Aqueous. Yeah.
So it must have had some other species that is a spectator in this case, so it doesn't matter, right, for me. So Cu2 plus is reduced because it moves from a 2 plus, it gained electrons. Gain of electrons is reduction.
Reduction.
Right? Okay? So I can just look at this. A voltaic cell itself is just an electrochemical cell, and it converts stored energy in the chemical bonds to electrical energy. Right?
So that would be an example of a battery. Okay.
This is a classic battery, right? Here, again, like I said, they don't have to be mixed together. They can be in 2 different containers, but we have to have something that allows electron to flow through a wire, and we have to have what we call a salt bridge to avoid the charged species from building up, right? And stopping the electrons from flowing across that wire. Here is the example of it. It's real. Here you can see in this copper and zinc, if you put a copper solution and you put zinc, right, inside of the copper solution, the zinc comes off and the copper jumps on, and you see the copper building over time on top of the zinc. So the zinc is actually exchanging, the zinc is becoming copper, right? It's being replaced by copper. So as the zinc comes off, it leaves electrons behind. The copper, that is a 2 plus, of course it was 2 plus in the solution, it sees an electron-rich area, it jumps on. So it's just a replacement, and zinc comes off, copper jumps on. Right? And then eventually this blue solution becomes nice and white because all the copper goes on onto the zinc rod, right? And replaces the zinc. So this is, again, another classic example of a oxidation reduction. But here now we begin to talk about anode and cathode, right? What occurs at the anode? Oxidation. What occurs at the cathode? Reduction, right? Reduction, if you know who is reduced, that is the cathode. If you know who is oxidized, that is the anode, because that's where oxidation occurs, right? These are practical stuff, right? Like when you have,
like when you have wires and you connected them, like you see movies sometimes and they try to connect the wires to get the car beginning, and you got a red one and a green one, and then you got the copper wire, and they're trying to figure out which one.
Well, that's coming off of a battery, right?
But isn't that like to say?
No. Not exactly. We're not bridging anything here.
Oh, so they're bridging.
Yeah, they're bridging to
stop. Okay, all right.
Right?
Okay.
But this is practical, like, all those pipes that run out of the city, right? You have to ground them, or else, like iron pipes. Over time they will corrode. So if you think about those pipes and these tanks that are under the ground, they're sitting there for many, many years. But they have to put a particular anode or cathode so that the electrons are flowing back and forth, right? That way the corrosion is reduced, right? But it's a practical application that takes place. Here you see like zinc is in one, copper is in the other. You have a zinc anode, you have the copper is the cathode. You can allow a current to flow. And you see the movement of the voltmeter. Because as the electrons flow, it flows through the voltmeters move from 0 to whatever efficiency that the electrons are moving with. See this thing here? This is what we call the salt bridge. If you don't have that, the current doesn't flow because the ions build up and stop the electrons from flowing. So for this whole system to work, you must have the cathode anode, and most importantly, the salt bridge. And the salt bridge doesn't have to be any of these ions, right? It can be some salt, any salt, right? Like for instance, the chlorine, right? And the potassium, flowing in different direction, but it's avoiding buildup of the sulfate in both cases, right? But this is what it looks like, and this zinc, and the surface of the zinc, right? The electrons are being lost, going up the wire, so as you lose electrons, the zinc comes off. It's oxidized, so it comes off in solution. The other way for the copper is different, because as the electrons come down and populate on the copper in solution sees electrons, and naturally they're going to jump onto the rod. So over time, what do you think happens to these two rods, the anode and the cathode, over time?
They start rusting, no? Oh.
No rusting taking place.
Oh, okay.
If I'm losing electrons here, right, and I'm gaining electrons here, right, what's happening to this rod?
Oh, it's going to get the product of the product on it? No.
They go to attract?
It's going what?
Attract?
It's gonna deteriorate.
Deteriorate. It's going to get smaller. This would get thinner.
Okay.
This will get bigger.
All right.
Because remember now, copper ions are jumping out and becoming copper atoms. So this is going to get bigger. This is going to get smaller over time. Okay.
Wait, go back over that again. Wait. All right, go ahead. Sorry. Sorry. It's okay, I'll read.
You guys ever hear about electrolysis? Not to pull out here and stuff. But it is, we use electrolysis to do, it's a kind of Voltaic cell, but we can use it to gold plate, right? You hear about cosmetic jewelry where it's gold and then you wear it for a couple, it looks nice, and then a couple of weeks after you're like, what's this? You look like you have plenty of money, you bling bling, throw that, right? Because after a while it just comes off. But we use electrolysis to put a pure metal on a surface, right? That is not really pure. This works with rechargeable batteries. This is where rechargeable batteries are coming from. Your phone, right? All this stuff that you see, right, with redox and stuff like that, that's your phone battery. That's your Tesla and your EV, right? Electrical vehicles, that's how they work, right? You have to recharge them, put energy back in them, put electrons back in, and then they build up until they're fully charged, and then you start using them again, and they discharge all the energy until you're ready to charge them again. That's the basis, okay, of all this, all these rechargeable batteries that we use out here, right? We know this corrosion. We see this all the time. You walk through the neighborhood, you look at the fence, and sometimes you look at the fence and it's rusting, right? And then you look at another fence and it's not rusting. What's on the other fence as opposed to what's on the fence? What's not on the fence that's rusting?
Oxidation of iron. No.
What's on? You have a fence that's rusting. It has all that.
H2O?
H2O would rust that down, man. What do we see on fences, man? You walk to the neighborhood, you have a wrought iron fence here, then this neighbor fence look like it's about to break down, like something eating it off. You see all the iron oxide, and then you look at this fence and it's really nice. What's the difference between them two fences? Guys, don't pay attention. See how this chemistry happening around here?
Oh, is it because, wait. Because some of them have this green covering over it.
No.
Okay, whatever.
We talk about iron, not copper. We talk about. We have. Thank you very much. You have paint. That's why we paint them.
Oh, that was it. The green thing that covered
What green thing? The green thing is paint. The green thing is you talk about color. No, but basically, yeah, we paint. That's why we paint iron.
Oh, okay.
To avoid water interacting. That is coming out the sky, right?
Ooh.
Right, a lot of water. So the water interacts with the iron and it begins to form this iron oxide. It's meant to protect. That iron oxide, that rust, is meant to protect the iron underneath. Right? After a while it gets water will erode anything on earth. Anything. It just takes time.
Universal
Right?
solvent.
Anything you put water in, it's going to erode it. But it might take a longer time for some.
What causes the car battery to get corroded on top of it when you got clean?
The white stuff that comes on top of it, that's coming from, I believe, the reaction that seeps out of it. So yeah, that seeps out of the cell, right? So you get that corrosion, and sometimes too when you look at it, it's the lead, right? The lead leads. So the lead is forming an oxide. So that would be lead oxide. So you gotta be careful with that too. You know what I mean? They said like a brush that you use to
I just put
clean.
like baking soda and vinegar on it and it just.
Yeah, okay. I'll try that, but I don't play around with car batteries. So combustion of fossil fuel, we saw that, and I spoke to you about this, natural gas furnaces, right? We spoke about that. If this doesn't go to complete combustion, we form carbon dioxide, right? Yeah, that's what we just spoke about. So that is another reduction reaction, right? This is an oxidation reduction reaction, believe it or not, right? All this time you're doing chemistry, you put these things on this, you light your stove, but you don't know you're doing all this combustion and oxidation reduction and stuff like that. Bleach, you use bleach, right, in your home, right? It's a very strong oxidizing agent. That's why it takes out stains and food stains and stuff like that. That's the power. That's what's happening here. You're really doing an oxidation reduction when you when you wash, when you stain up your white clothes and stuff with food and anything because you can't eat properly, right? What else? In your body, right? Oxidation reduction is taking place in the metabolic pathway, right? I hate chemistry. I hate bio. I'm telling you. I should hate my wife.
You know what?
She's
You
a
know
biologist.
what?
She represents everything I hate in chemistry.
Wow.
Well, you chose to marry her.
Thank you. With her.
But you know what? Who tell you that she didn't cheat me?
You're right.
Okay. So break down molecules into
It's mad right here.
the metabolic pathways. Y'all don't start with me. Right?
can't
It's enzymes, right? In that you have oxidation, you have reduction, and stuff like that. One day she'd cover you guys.
Oh, we would love it. We're going to tell her everything you said.
Y'all would know it's her.
Oh.
How would we know?
Okay, you would know. Chemical, right? Mike.
How look?
She look like a microbe.
I'm going to tell her what.
She look like a microbe. Okay, so antiseptic and disinfectants. We know hydrogen peroxide very well, right? There's a reason why we're in hydrogen peroxide, why we put it in a brown bottle. You know why? Why it's in a brown bottle?
Protected from light?
Yeah, because it will break down.
Wow.
It will if it's exposed to light, it will just break down into water. Right? It just becomes water. So that's why they do that. So here's the deal. I think
God, we're tired.
we leave this because this is going to. We leave 4.9
No,
and
sir.
start to 5. Listen, y'all had a whole break.
Oh,
man.
God, man.
A whole week. We're going to do something. Hold on. Stop fussing. If you're fussing, just go to this now because I can watch this in 2 minutes and tell you who Marie is.
Yeah, yes, that would be good. Yeah, we do that. Me no
It's not
want.
going to take 2 minutes because here is where we really have to focus on balance equations, coefficients and stuff like that, because here's where we look at a theoretical, right? The theoretical equation, and determine if I start with a certain number of grams or a certain number of moles, this is the number of grams of product, right? So we have to treat this next week in a better way, because that's where the pharmaceutical companies, and we're using chemical equations to do that, right? You have to be able to really pay attention, because all this that we learned today, formula mass,
This is why.
and all this stuff here.
Could you teach some more?
This is where everything lies. This.
Can we get more lecture?
Oh, you don't want to do this?
Nah.
Fine, let's go. We finished. Right, no problem.
Are you
We can do this
causing?
next week. Because some of this lies on and what we did today.
Okay.
Okay, so next week, this would be, because you'd have to crack your head a little bit more. All right, so listen, then let's just talk about this, and then we might, we do some questions tomorrow, because these questions, next time, because these questions that come off of this embraces the whole chapter.
Okay.
Right? Alright, so we have to know how to calculate quantities of reactants and products, because we have to really know what is it that we're getting. What are we getting? So we need a balanced equation to start with. If you don't balance the equation, you can't do these problems. So the first thing you should do when you have a stoichiometric problem, or a problem that's asking you to use a chemical equation to determine the amount of reactants or products needed, you must balance it. You cannot go anywhere without balancing. And the coefficients, of course, represent the number of moles. So it speaks in moles, not grams. That's why when you're doing these problems, you cannot start with grams. If you're given grams, you must calculate grams to moles to start this problem.
Okay.
And then you go back to the grams.
And then if it's grams they want, then
you
you
go
have to
back.
calculate grams to grams.
Wow.
Okay? So the chemical formulas of all reactions and products must be known. Equations must be balanced to obey the conservation of mass. Calculations of unbalanced equations are meaningless. I won't even look at it. Once it's not balanced, I'm not even trying to look at it, right? The coefficients in a balanced equation represent the relative number of moles of products and reactants. So equations speak in terms of moles. 2 moles of hydrogen reacts with 1 mole of oxygen to give you 2 moles of water. Right? We don't speak grams here. Right? They can give you grams, but you better convert grams to moles to start these problems, right? So herein you have 2 moles of hydrogen reacts with 1 mole of water to produce 2 moles of water. 2 moles of oxygen to produce 2 moles of water. If you have 4 moles of hydrogen react with 2 moles of water, it gives 4 moles of water, 2 moles of oxygen, right? We can look at it simple, right? From those simple perspectives. Now, here's the deal. If we're looking at water, right? It's a balanced equation. How many moles of O2 are needed to react with 4.26 moles of hydrogen gas? Factor labor method. Y'all remember that?
No.
Oh yeah, we work this down to the bone. Conversion factors. That's what they are, right? Right. To perform calculations here. For instance, here's the reaction. You have 4.26 moles. It's given. You have the chemical reaction, then you want to know how much moles is produced.
Oh, it's half of
This
it.
mole, this is half.
Yeah,
Yes,
it's half.
because they divided by 2.
Wow.
Now, here's the deal. I like to give students different pathways to do this. So here's the deal. Here's a pathway, right? I have 2H2 plus O2 gives me 2H2O, right? Originally, they tell me it's 4.26 moles. This says 2 moles of hydrogen reacts with 1 mole of oxygen to give me 2 moles of water. They want to know how many moles of oxygen must react with 4.26 moles of hydrogen, right, to give me this, right? Now, watch this. It is a ratio and proportion problem, right? Because they gave me moles, they gave me 4.26 moles of hydrogen. So it's a 4 to 2. Remember, this is 1. But this is my unknown over x. So when I pull this out, it's 4.26 over 2 is equal to x over 1. Can I solve for x? 4.26 divided by 2. X is moles of O2. That's my unknown. Right? That's what they asked me to find. So x is equal to 2.13. Either way, the problem works. You can work that way, but here's where the 2, you see this 2 here? That's the stoichiometric ratio, right? It's 2 moles of hydrogen to 1 mole of oxygen. That's where this factor label comes in. But it is the same thing right here. Either way, it doesn't matter. But this cannot be grams. It must be moles because moles speak to moles.
Okay.
Grams don't speak to moles. You cannot do that. So if you're given grams, you must convert grams to moles to start this equation, to start this process. But this ratio, right, they asked me for oxygen, so oxygen has to be in the numerator, right? The moles of hydrogen has to be in the bottom because I'm canceling out moles of hydrogen, but this is the same process as well, right? It's amazing that you want this. High school students would do this all day long. Wow. So here's the deal. Convert between moles to grams, right? Here, moles of oxygen to grams of oxygen, right? How are we going to do that? You find the molar mass of oxygen, which is 32 because it's 16. 16 plus 16 is 32, right? So we have a conversion factor here. It's 1 to 32 or 32 to 1.
It's 32.
Right? So now, when we set up this equation and we solve it, 1 mole of oxygen is equal to 32 grams of oxygen. Remember, it's O2. Because if you don't do O2 and you do O, you're going to get 60. And it's not going to be good.
That's
right? So here, it requires only molar mass. They convert that, right? You go from grams to moles, and you can go from moles to grams. So here, if you look at moles of a product, right? We just did this equation, right? No, a similar one. Similar one, right? What is this telling me? Is that you have 5 moles of O2, talking about it the other way, is consumed, right? So here we know that oxygen, 5 moles, O2 consumed is a 1 to 5 ratio between methyl propane, right? This is propane. Between propane and oxygen, it's a 1 to 5, right? Between carbon and water, right? It's going to be a 3 to 4. Between propane and carbon dioxide, it's a 1 to 3, right? It's 1 mole to 3 moles, 1 mole to 4 moles, right? So when we're looking at limiting and excess reagents, right? We can look at the relationship between the gas to the oxygen, gas to the carbon dioxide produced, and gas to the water produced. Because the gas or the oxygen could be in limited resource. It could be a limited resource, right? So you have to look at what the problem is asking you for. It says here calculate the grams of O2 reacting in 1 mole. Notice they say grams. Because what the equation gives you is moles.
Yeah.
When you use the equation to do the problem with the ratio, look back again, the ratio is given in moles. So what you're going to calculate is moles, but then you have to, they say no, bring it to grams. So here, you have to move moles of propane, moles of oxygen to moles of grams. So you got to figure out what's the relationship between the ethane and oxygen. Then you get oxygen grams, you calculate that. Now here's the setup, right? So you have 1 mole of propane. It's 5 moles of oxygen to 1 mole of propane. If you go back to the equation, it's a 5 to 1 or 1 to 5, right? So that conversion factor is there. Then all you have to do is multiply by the molar mass of oxygen, and you get 160 grams of oxygen, right? Okay. If we go the other way, this way, for those of you who may want to see a different method, C3H8
Yeah, right.
plus 5 moles of O2 gives me 3 moles of CO2 plus 4 moles of H2O, right? Here's the deal. I'm looking at the fact that we're using 1 mole. Where is it? I'm using 1 mole of propane, right? So this is a 1, right? This is a 1, right? It's 1 mole, 1.00, right? But they're asking me for grams of O2. So this has to be my X, right? So you see the 5 to 1? When I pull this out, it's 1.00 over 1 is equal to X over 5, right? It's the same 1 to 5 ratio, okay? When I do this X, when I solve for X, that's moles of O2. Do I remember that? What my X represents in this case, when I'm doing it like this. So now, it's going to be 5.00 moles of O2, right? See it right here? Is it 5? 1 times 5 is 5. That's a 5 right? All I gotta do here now is multiply by the molar mass of oxygen, which is 32.00 grams per mole of O2. Grams of O2, grams cancel, 5 times that guy, right? 5 times 32. Same thing. Same thing.
I just have a question. You said everything's so the 5 in front of the O2 is the moles
That is moles of O2 in the reaction.
in the reaction.
Yeah.
Okay. And we're trying to find.
You're trying to find grams of O2, right? But we have to start this because equation speaks in moles. Everything has to be done in moles and then converted to grams. Make sense? So either way, if you use this, and if they are asking me for H2O, it will be a 1 to 4. That's only to, and then I'll just multiply by the formula mass of water, which is 18 point. Anybody remember? 0.02. You gotta always remember that you don't have to calculate water over and over again, right? That you should hold in your head, 18.02. Once you do it once, remember it, right? So that's the process here. But this is how they're telling you, if I start with 1 mole of propane, how much moles of oxygen can I get? Based on this balanced chemical equation, all right? And the rest is just the same thing over and over, right? Because here what they do it for the carbon dioxide, right? The carbon dioxide is a 1 to 3 ratio. You see the 1 to 3 ratio here. Here, they do it for water. You see the 1 to 4 ratio here as well. But here's the deal though, this is a little bit different, right? They gave you 36 grams of water. This is where you have to be very careful because you have to convert grams to moles. This gives you, this calculation right here gives you moles of water. And then now you can go on to find out the grams of propane that is required
To produce.
to produce that much grams of H2. So it goes back. They can ask you for the, how much of another reactant is needed, or they can ask you how much of a product is produced, how much is yielded in this chemical reaction. But the key here, folks, is that you cannot use grams. So you couldn't come here and put 36 grams. It's not gonna work. Because this equation will speak in grams. It will never speak in grams. You have to change grams to moles. That's the subtleness of this, right? See, everything is moles. Even though it started with grams here, this conversion brought it to moles. And then you use a stoichiometric relationship of the 1 to 4 to finish the product. Okay? And these are just like doing the same thing, right? And this is just how we move from grams to moles, right? To moles of C, and then we can come from grams of A, moles of A, moles of C, to grams of C. This is here, this is a gram-gram problem. We call that a gram-to-gram problem. They gave me grams to start. I must change to moles, use the stoichiometric relationship, get moles of C, then use the gram formula mass or the molar mass to get to the grams of C. That's a gram mole problem. So they gave me grams, I changed grams to moles, and then I use the stoichiometric relationship to get moles of the product. Right? So those two problems, you can get moles to grams, moles to moles, grams to grams, and grams to moles. They can throw it anywhere to you. Okay? All right? Good. Yeah, go home.
Thank you, Lord.
Came in late.
Oh, yeah, me.
I'm letting you out even early.
Yeah, thank you. You see how it works? You see how wait.
Don't go nowhere. Don't go nowhere. I think it would be nice to. Oh Lord. Oh.
Oh, Lord. What's this? Percent
Hold
yield.
on. You can read this up, percent yield, right? It's just the actual yield over the theoretical yield. What we get from the chemical equations is the theoretical yield.
Yeah.
Right? So when we do this calculation, this is theoretically what we should get. But when we go into the lab, that don't mean that's what we're going to get because we incur error.
Yeah.
Right? And sometimes the things just don't work the way we're supposed to work, temperature, pressure, variation. But when we're looking at a percent yield, like this is what pharmaceutical companies do. They use the equation, get the theoretical yield, go into the lab, do the chemistry, the experiment, then they see how much they got, and then they divide the actual yield that they got in lab to the yield that they got in calculation. It gives them a percent. At 94.7%, that's big money for pharmaceutical companies. If that's not in maybe like the 80s percent, they're not going to do it. It's not going to be worth it money-wise for them, right? Okay.
So that yield. So it was 90. It was 94%.
That was net. No, in whatever this was, this came out to 94.7%. So this is good. This
Right.
is very
Good. Yes.
for any chemical equation.
Right. For the yield that was produced. There you go. Okay. Got it.
Okay.
Yes.
Some people came in late. You know who you were.
Nemard.
So let me see. I've got Chung.
Thank you guys.
No, that's Chung.
Thank you.
Clark,
See how hard it
Chantel.
is. You know me fully
If you
done.
came in late, don't go. Dobson.
You know say me fully done. Anyway, it's over.
Delilah.
He nice though, the professor. Yeah, man, cute. He is clean. You know, everything we do is fun. Everything we do.
Jean,
Class, cooking, singing.
King, Nikita,
Ingrid, I love you, baby. I told you I was taking you with me. You think I drove me? I make you come everywhere with me. School.
Loretta.
Yes, here. Everything.
Robinson,
You hear him?
Katrina,
Anywho, it was fun. Thanks for joining me, guys. You know I love you, lifers. I love you guys. At least we'll learn something today. Good. I soon get home. Love you. The class was good.